Okay, the recording is now going, so please go ahead.
I'm gonna share my screen fast. Let me know when you can see it.
Yes, I see your screen.
Okay, yeah. Thank you everybody for joining. As Nicholas kind of mentioned, my name is Ram, and I'm part of the Azure Trustworthy Machine Learning group at Microsoft. This work was done in support with other members in my group: Magnus Nystrom, John Lambert, Andrew Marshall, Mario Kurtzel, Andy Comisnero, Matt Swan, and Sharon Xia. And as kind of like Nicholas alluded to in the introduction, this paper might be different in terms of like what's happening in this workshop. It's more like an informational interview. So we have like two contributions in this paper. So we conducted like an industry-wide survey to kind of investigate how organizations are prepared to tackle adversarial machine learning. And through these informational interviews, we kind of like outline some gaps in the current existing security development lifecycle, so that when an ML engineer or a security responder is tasked with developing and deploying machine learning systems, what are some of the open questions or gaps that they're feeling out today. So I'm going to today focus on the talk on the highlights from our first contribution, which is the industry survey section. So before I start off, I want to tell you that my group is hiring. So if you're an adversarial ML researcher who wants to work in an enterprise setting, please reach out to us. We definitely want to kind of like chat with you. So the agenda for today's meeting is I'm going to start off with the problem statement and the motivation, kind of lay out the methodology of our informational survey, kind of give you like our top insights, and kind of like lead with the next steps. So, the first thing that what we're seeing is that companies like Google, Microsoft, Intel, and IBM are kind of outlining principles on how they're securing their machine learning systems that is separate from how they're actually securing their traditional pieces of software. So if you go on sites today, you can see like the responsible AI practice in Google, where they very comprehensively lay out the security principles. Microsoft's got a separate one. So it's kind of very interesting to see how this is almost turning out to be the industry's next big race. But it's not just the large organizations. Startups are now mushrooming to kind of help secure enterprises of their machine learning systems. So for instance, Robust Intelligence, which is like a startup that I mentioned, really kind of puts it front and center as to how they're empowering engineers to go after, to build like secure machine learning systems. And a lot of this has been fueled by Gartner. So Gartner is kind of one of the leading market research firms that actually has a lot of sway in how C-suite executives invest in security. And in 2019, they released a report kind of alerting how ML models can be manipulated. I mean, this is like not news to anybody who's joining this call, but but our hypothesis was, how prepared are these organizations for attacks on machine learning? And we kind of thought that, hey, organizations are kind of reasonably prepared to tackle adversarial ML problems. And we kind of had this like gut intuition, based on like 5 reasons. I'm going to first make a case as to why organizations should already be reasonably prepared for adversarial ML. So the first thing is, machine learning is rapidly becoming core to organizations like value proposition. Like PricewaterhouseCoopers kind of said that, hey, ML systems are like the annual growth rate that's been projected for ML investments in 2020 is 39%. And it's only natural that organizations that are investing in machine learning systems, especially for their core business value proposition, are protecting their crown jewels. The second thing is there's been like in the last 3 years, there's been like an uptick of like attacks in marquee companies that are investing in machine learning themselves. Say, for instance, Google, Amazon, Tesla have all to certain degrees faced some sort of like adversarial attacks, either from researchers. And this could really be a bellwether of the rise of like adversarial machine learning for enterprises. Interestingly enough, on a very similar note, adversarial machine learning is now like entering like what we think of as like mainstream infosec. So recently, a CVE was announced wherein Will Pierce, a researcher who goes by the handle Moohacks, stole like ML models from Proofpoint, which is like an email protection company. He performed like an offline evasion attack and then mounted an online evasion attack to bypass Proofpoint's email protection ML models. So like for the first time, like a CVE was kind of issued, and these CVEs are generally consumed by, I think, of like traditional security analysts. And CERT very recently kind of like issued a very broad vuln note on like how like ML systems that are trained via gradient descent are just vulnerable to arbitrary misclassification attacks. So all this kind of like shows that, you know, adversarial ML is just like real and kind of have like tangible impact on not just like organizations' security strategy, but overall for like rank and file security analysts. And you know, finally, another reason why enterprises might already be investing in this is standard organizations like ISO and NIST are forming these like certification rubrics to assess security of ML systems. And whether we're not going to debate if they're going to be like technically sound or not, but historically, these endorsements by these standard organizations have been historically sought after, and their like seal could potentially be lucrative for a company that's trying to stand out. So if you are like you know, an enterprise that's offering like an ML system, like having that ISO standard that your ML system is trustworthy can kind of like help you stand out from the rest, or at least like make that as the industry baseline. So also like governments are showing signs that industries will have to build ML systems securely, with the EU actually releasing a complete checklist to assess trustworthiness of ML systems, which could potentially snowball into regulations. And finally, like, you know, this is a slide that I'm sure like all of you are familiar with. There's a surge in adversarial ML research. And we as researchers know that ML systems are vulnerable since 2004. Now the question is like, does it make sense that industry is also keeping up with this sort of trends? So we set out the survey thinking that, folks, you know, with the hypothesis that the organizations are making small improvements towards protecting their ML systems. And the top takeaway is that it's almost like a negative result. Like we found that organizations are really not equipped for adversarial machine learning. So there's one takeaway that you take from this talk is that you can really make an impact if you're part of like an ML company who's trying to build ML systems. So I'm just going to dig through like the methodology of how we did this survey. So we spoke to close to 28 organizations. 18 of them were large. By large, we mean like they employed more than 1,000 people. And 10 of them were like small and medium-sized companies. Mostly, these 28 organizations fall under what we put under the security sensitive bucket. So 22 of them were either in finance, in cybersecurity, in healthcare, or in government. You know, the remainders of them were in like things like urban planning and food processing. So we chose these organizations specifically by finding out like in either based on their blogs or based on their earnings report, if they have kind of like made it appear that ML systems is core to their business value proposition. And at every organization, we spoke to two personas. We spoke to a machine learning engineer who's responsible for developing and deploying the machine learning systems. And we also spoke to the security analyst persona. So they are the ones who are responsible for detecting, responding, and remediating against threats against a machine, against like a piece of software that might have been compromised. So imagine like, their security analysts are kind of the frontline responders when an attack is happening in a company. Now, in some of these organizations, like there was no clear demarcation between like ML engineers and a security analyst, especially for like startups and small mom and pop companies. They might have just been like one person playing multiple roles, but for broadly, we did try to suss out like an ML engineer and a security analyst persona. And there were three big themes in our survey. We set out to find out like three things. So what is the process the organization is following currently when it comes to securing ML systems? The second thing is like, what kind of attacks impact their organization most? And the third one is, if their ML system was under attack, how would the security analyst approach it? So if there was like a Heartbleed style like vulnerability that was exploited, but in the context of a machine learning system, how would the security analyst kind of like respond and remediate against these kind of like attacks? Now, before I dig into the insights, I first want to contextualize this with the limitations of our study. So the first one is that we only spoke to 28 organizations, and they do not represent like all branches of industry. Specifically, we did not speak to folks from self-driving cars. So they're not part of our population. The second thing is that we did not account for like geographic distribution. Most of the organizations we spoke to were kind of like headquartered in the US or Europe. And we did not investigate like broad safety failures or even like unintentional failure modes like reward hacking. So we assumed that these failures were like caused by like a malicious adversary who's trying to subvert the system. So I want to kind of like put this slide in to kind of show, to contextualize the insights that we got in our study. So the first one is that we found that as one security analyst kind of put it, like their top threat vector is still phishing and malware on the box. To quote one of the analysts, they said that this adversarial machine learning looks futuristic. And the takeaway here is that while there's great interest in adversarial machine learning, only 6 organizations, all of whom who are large or government, have kind of like assigned headcount to solve this problem from an engineering perspective. The second insight is that there's a lack of know-how in the industry when it comes to adversarial machine learning. So 22 out of the 25 organizations we spoke to said that they do not have the right tools in place to secure their ML systems and are kind of like explicitly looking for guidance when it comes to helping engineers to develop their ML system securely. The third insight is that we asked each of these organizations to kind of like pick one attack from the list of 13 that we had, the 13 buckets that we had, and they were allowed to just pick one attack that would impact their organization most. Data poisoning really came up at the top. It's kind of caught the attention of the enterprises. As one of the medium-sized financial tech told us, that they use like machine learning systems to suggest tips and financial products for their users, and they're really worried about like inappropriate recommendations like attack on Tay. The organizations are also really also care about like model stealing, as it could lead to loss of intellectual property. Large organizations are kind of like employing especially data science teams and paying them NFL style salaries to build bespoke systems. for their business needs, which is generally touted as a competitive advantage. And one of the large retail organizations told us that they run a proprietary algorithm to solve their problem, and it would be really worrisome if somebody can just like outright engineer it and put it out on Pastebin. The last one is like model inversion. You know, organizations really care about like attacks that lead to potential breach of privacy. So like one of the banks told us that they want to protect like their client information and employee information used in ML models, but really they don't have like a plan in place to do that. So some of the things that's notably missing over here is that adversarial examples in the physical domain really resonated with the respondents, but did not rank high on our list. Like one reason is that the organizations that we spoke to, like I said, did not have a physical component like cars or drones. The next one is that for security analysts, there's really a mismatch between expectations and reality when it comes to adversarial machine learning. Security analysts in particular kind of expect that algorithms that are available in platforms such as like Keras, TensorFlow, or PyTorch are inherently secure against adversarial manipulations. And security analysts kind of expect that these algorithms have already been battle tested against adversarial ML attacks. This is perhaps because like security analysts who've mostly been exposed to traditional software kind of assume that libraries that have been put out by large organizations would have already been like security stress tested, which may or may not be true. And finally, like respondents really did not know what to expect when systems get attacked. So security analysts today have a well-defined playbook when an ML system, when like a traditional piece of software is under attack, but when like a machine learning system's under potential attacks, they really did not know like how to update their like incident response playbooks. And there are also a lot of open questions for them to figure out. For instance, what does forensics of like a machine learning system look like? Or like, what does it mean to patch an ML system that's been under attack? So all this to say that, you know, in terms of like next steps, so Nicholas Carlini kind of like in his keynote in 2019 at Camlist, kind of like likened the current state of like defenses and adversarial ML to crypto pre-Shannon, you know, as a comment on the ease with which defenses are broken. You know, we kind of like think that this metaphor is apt, that just goes beyond attacks and defenses. Like from our informational interviews with 28 organizations, we think that most ML engineers and security incident responders are unequipped to secure industry-grade machine learning systems against adversarial attacks. And you know, perhaps it's kind of like time to inherit like the structured security development process of like traditional pieces of software. And that's kind of like some of the gaps that we kind of elicited. So with that, that's kind of like the end of my presentation. So if there's thoughts, comments, we'd love to hear from you.
Sorry, I had my mic muted. So there's currently no questions in the Q&A. Feel free to ask them. Okay, great. We just have a first question now. So do you want to read the question and then answer it?
Yeah, so Konstantin Berlin asked, you mentioned that most organizations don't have a plan to protect against ML attacks. What would be a suggestion for defense against it? I think that's a great question. I think one of the in Google's like responsible practices for security, they kind of very nicely mentioned that this is an active area of research and it's hard to prescribe any sort of defenses at this stage. And they kind of point to how there should be defense in depth. At Microsoft, we published kind of like a threat model guidance for engineers to follow when it comes to machine learning systems. And for security incident responders, we have like a playbook that we published as well as a bug bar that's part of their incident response process. So from that angle, there really isn't like prescriptive defenses.
It sounds like Lorenzo has a question. Maybe you can ask it live.
Yeah. So very nice talk, and so Lorenzo Cavallaro here from King's College London. I was quite surprised when you had your slide about the top 10 threats that the companies fear. So one is poisoning, and then model inference and model inversion, if I remember correctly. So this is quite interesting because in at least in academic context, it seems that we're still playing quite a lot with evasion attacks, and I'm just wondering whether. So I've had conversation as well with collaborators in industry, and the feeling is that they don't see that completely as a threat now because there's no real end-to-end system, and also because the systems are not really made but just by one system, and there's a pipeline that you need really to break into it. So can you share some other insight into this? Why there's no in the top 3 like this evasion?
Yeah, definitely. I think like we were surprised when poisoning came up to the top as well. When I'm looking at my paper, there were like 10 respondents that kind of mentioned poisoning. I think there could be like, a couple of things. First of all, I can give you like my educated guess. It's perhaps because of the cultural significance of Tay. But if you kind of like know that, people are kind of worried about the ease with which poisoning attacks could be potentially done. Like for indiscriminate like poisoning attacks, they're worried about like people with little to no skills, like script kiddies, in their mind could mount like poisoning attacks, which may, which is obviously not always true. So from a threat model perspective, if all it takes to topple their like large investment or script kiddies or post and Reddit and Trojan, that is pretty scary for them.
So it looks like there are a bunch of questions that are now in the Q&A. Unfortunately, we only have time for one of them. I like Dave Evans' question on legal risks, but feel free to pick any of the ones that you think is best.
Oh, totally. Yeah, I'm happy to like talk about legal liability. So, another paper, David, and I'm happy to like send you a link. We kind of explored how should law respond to adversarial machine learning, and we looked at it from like 3 angles. Like, how does the Computer Fraud and Abuse Act, does that like that's the traditional like U.S. anti-hacking statute? Is it a good coverall for adversarial attacks? Yes and no. For some things like poisoning, or like adversarial examples, like the Computer Fraud and Abuse Act might work out, but it's not a coverall for sure. There are definitely like things wherein the traditional notion of access and authorization that the legal standards kind of hold may not directly always apply to, say, like all sorts of attacks. Now, when it comes to like stealing like an ML model, like we try to like see if the copyright laws can like put backstop around it. And again, because there's no case that's gone to trial and like there is no like legislation that's passed, it's also like still up in the air. So we really don't know for certain if like legal liability issues for ML vulnerabilities can be covered by existing legislation.
Okay, great. I would encourage all of you who have additional questions to ask them in the Slack. I will leave the questions still open here, and you can do that as you have time.
Okay,
so
awesome. Thank you.
with that, thank you for giving the talk. It was very nice. And we will move on now to the next talk. The next talk is adversarial attacks against LipNet, end-to-end sentence-level lip reading. And Mahir is here, or Derek is here to give the talk.
Hi. Let me see. Right.
It looks like we lost Derek. Well, Ram, do you want to take one more question while we get our other speaker back, and then hopefully we get him back in just a second? Great, actually we have him back. Okay, Derek is back.
Sorry about that.
Oh, that's a problem. We've all have had internet problems over the last couple of days.
Let me see. Let me get this. All right. Can you guys see my screen?
Yes, we can.
All righty. Okay. All right. Hi, I'm Derek Tang. Today I am presenting on behalf of my partner, Mahir Jithanandani. I will discuss our paper, Adversarial Attacks Against LipNet, which explores different targeted and untargeted attacks on Google's state-of-the-art lip reading model, LipNet. Before I begin, I want to briefly talk about the motivations for this research, which began as a project for a deep learning class at Berkeley. As surveillance systems have increased in power, we think that lip reading software will become increasingly advanced and important. So it really is essential to understand how these systems can be both manipulated and attacked. Moreover, we think that our research is not only constrained to just the lip reading domain, but also demonstrates how other video classification systems could potentially be attacked with similar methods. With that being said, in this presentation, I'll do a walk through some of the more technical details of our paper and present some of the results that we arrived at. So first, we introduced the LipNet model that we performed our attacks on. As you can see, the model is fairly complex. It takes in a short video of 75 individual frames. Each frame is 50 by 100 pixels wide with 3 channels for the RGB colors. The frames then go through a spatial temporal CNN, a bidirectional GRU, a linear layer, and then finally through the CTC loss function. LipNet works on the grid corpus, which is a highly structured sentence dataset consisting of 1,000 fixed sentences. So for constructing adversarial examples, we're immediately interested in the loss function, which in this case is a connectionist temporal classification, or CTC loss. And CTC loss is used when the sample has no specific alignment as well as variable length, which in this case for lip reading obviously applies. The technical details of the CTC implementation are not as important as the fact that the loss is smooth and differentiable, which allows us to use our white box adversarial attack techniques based off of finding the gradient. So real quick, I just want to show an example of LipNet in action. On the left, we have a video of a speaker with audio.
Set white with P2 soon.
And on the right, we can see how the LipNet model classifies this video with complete accuracy. So our goal here is to create targeted adversarial attacks. Given some video sample X with a true label as Y, we would like to find an adversarial sample X prime where the network output F of X prime is T for some target phrase T in the corpus. Additionally, it's important that our adversarial sample X prime is not visually distinct from our original sample X, and that we can perform these attacks consistently for different target phrases with high confidence. So there's already been a lot of existing research on adversarial examples in the image domain. Models that classify data sets like MNIST and CFAR have all been shown to be susceptible to gradient-based adversarial attacks. There's also been some research into black box and white box attacks on video systems. However, no real research into the domain of lip reading specifically. And finally, Nicholas Carlini, who's with us, and David Wagner have produced research on temporal audio attacks that have helped really steer the direction of our own research, given that they too dealt specifically with the CTC loss function. So we just want to start briefly talking about untargeted attacks. So the untargeted attack that we want to introduce is called the fast gradient sign method. The idea is essentially to increase the loss between our original sample and the true label Y. And we can do this by taking a step in the direction away from the gradient between the loss of the function on the true sample X and the true label Y. And this is called, again, the fast gradient sign method. We can see that our update function is essentially taking the sign of our gradient and clipping it by some epsilon value E to create a perturbation that we add to our X to arrive at our adversarial example X prime. So we ran this attack, and with an epsilon value of 0.025, we can change the classification of our original sample, set white with P too soon, to an entirely different sentence, set red with X7 now. And here's a frame that's randomly extracted from both the original sample as well as the adversarial example. You can see that they do look very similar, but slightly different when looked at close up. However, when the video is played, these frames move quite quickly and the differences are nearly indistinguishable to the human eye, and we shall see this in an example later. So after showing that we could successfully create untargeted attacks, we wanted to move to the targeted domain. In order to create a targeted attack, we essentially need to solve the minimization problem presented here. We can think of our adversarial example as our original example, X, plus some perturbation, delta. We want to minimize delta over some distance metric P to be indistinguishable to the eye, while simultaneously following the constraints that our original X plus the perturbation must be valid, i.e. must have pixel values mapped between 0 and 1, and that F of our adversarial example, in this case, the network's output, must be equal to our target phrase. So the first targeted attack that we explore is called the iterative fast gradient sign method. And this attack approximately solves the minimization problem from above using the L infinity norm as a distance metric. This method is very similar to the fast gradient sign method from before, except we use many iterations, and instead of stepping away from the gradient with respect to the true label, we instead step towards the gradient with respect to the target label. You can see these changes reflected in our update rule, where our A represents the number of iterations, and our each iteration we have a smaller perturbation in the direction of our target label. This is essentially a version of gradient descent where you're projecting onto the L infinity norm ball at each step by using this epsilon clipping technique. And using this attack, we tested approximately 15 target phrases and found that with an epsilon value of 0.025, we could reach convergence with consistency within 20 to 30 iterations, which is quite fast. This creates adversarial examples that are at most 2.5% away from the original sample, given that our epsilon value is at 0.025, which means we know that our adversarial video is at least 97.5% similar to the original video, which isn't bad, but maybe we can do better. Now, before we move on to our next attack, let's revisit this minimization problem from before. Now, wouldn't it be nice if we could simply differentiate our objective function and perform something like gradient descent? Well, the main obstacle here is the second constraint that requires the model's output, given our adversarial example, be equal to our target phrase. And this is where Carlini and Wagner's work comes in. Carlini and Wagner show in the research that if we choose the L2 norm as our distance metric, we can reformulate this minimization problem by bringing the constraint into the objective function as the loss of the adversarial example with respect to the target phrase multiplied by some hyperparameter C. We can now look at this objective function in two parts. First, we want to minimize the perturbation, And then second, we're trying to minimize the loss of the adversarial example with respect to our target. Intuitively, if we're minimizing the loss of our adversarial example, we are telling our objective function to find some delta such that x plus delta is close to our target. So because CTC loss is differentiable and smooth, we now have a differentiable objective function, and we can perform simple gradient descent. In this problem, instead of constructing our adversarial example as we go, we are now solving directly for delta, or our perturbation. So we're taking the gradient with respect to delta, as you can see in our update rule. And we employ some learning rate gamma, just like gradient descent would do. So this is a more precise formulation of the problem than the iterative fast gradient sign method from above, which leads to smaller perturbations, especially because using an L2 norm as the distance metric means that the pixels that don't really matter will be more so unaffected, whereas with the L infinity norm, any non-zero pixel change will be weighted equally, as it just gets clipped by the sign. So when performing the attacks with the Carlini-Wagner minimization problem, our main job is just to tune the hyperparameter C and the learning rate gamma. So the hyperparameter C is quite important here. It determines the relative importance of being close to the original video versus being adversarial, where a larger C emphasizes loss minimization and makes the video closer, but might result in perhaps a larger perturbation, whereas a lower C might result in a lower perturbation, but might not necessarily converge to exactly the desired target phrase. After testing multiple values, we found that we got the most success with setting C to 0.1 and the learning weight to 0.1 as well. We eventually ran into the problem of oscillating solutions after around 50 or so iterations, where we would get an oscillation between the target phrase we wanted and a target phrase that was similar. In order to fix this, we used a learning rate decay of 0.1 after every 30 iterations, while simultaneously increasing our C value by a scale of 10. And the reason we do that is because we found that introducing a learning rate decay helps with convergence when the loss is sufficiently small, but oscillating. And the reason why we increase C at the same time is so we can put more importance on minimizing the loss with respect to the target versus keeping our perturbation small, since after 30 or so iterations, our perturbation is already quite small. And this method actually helped prove very effective in both speeding up the convergence as well as leading to more consistent solutions. So I just want to show some of our example videos that we were able to construct. So again, this is the original video. And with the CW attack, this is the adversarial example that we generated, where the target phrase was lay red by Q0 please, and this converged in around 40 to 50 iterations. And as you can see, this is nearly indistinguishable to the human eye. You really can't tell too much of a difference from video to video. So again, this is an extraction of one specific frame of the two videos above. You can see that this black frame represents our perturbation. You can see that the pixel changes here are the non-black values. And in this specific frame, you can go in and analyze where the attack is changing the pixels in order to create the adversarial frame. And this also is a benefit of using the L2 norm as opposed to the L infinity norm. You can really go into certain keyframes and see which pixels are important to changing the prediction from the CTC loss for each frame. So again, just to compare our iterative I-FGSM method as well as the CW attack, this is our video perturbation from the iterative attack. And this is the perturbation from our CW attack, which you can see is smaller overall, as well as more concentrated in certain regions. So after testing around 10 to 15 target phrases for both methods, we found that we can consistently get convergence to any target phrase that we chose within the corpus, as well as modifying things like sentence length, but not without modifying the actual grid structure. The iterative FGSM was able to converge quickly with an epsilon value of 0.025 or greater, whereas the CW attack took much longer to converge, around 40 to 100 iterations often, but would produce a perturbation that was much smaller than the iterative FGSM. On average, there is a pixel change of about 0.0033. So on average, a video would be, an adversarial example would be 99.7% similar to the original video, which we think is pretty good. So obviously, some of this work can be expanded on, given that our grid corpus is fairly limited. However, we believe that as the better LipNet, the lip reading models advance, that attacks will also be able to be developed for those as well. We think that it's interesting that we think it would be interesting to see if some of these white box attack might be able to be transferable, as has been shown with other non-video based gradient attacks. And finally, we think that there might be different ways to optimize our gradient descent methods that might lead to faster solutions, and specifically in the context of our CW attack. And yep, that's pretty much it. And I'll take any questions.
Great, thank you very much. So if there are any questions, please feel free to ask them in the Q&A or post them in the chat. We have a comment from someone who says, wow, that's super cool. So that's nice.
We thought so too.
So maybe while everyone else has a chance to write a question in the Q&A, I'll ask one to start. So the method you have works reasonably well for lip reading. Do you think that if you took a video of a person talking, that it would be possible to jointly attack the lip reading and the audio?
Yeah, so we've definitely come across some systems that use both audio and visual to classify lip reading prediction. We think that, I think that I don't have a great understanding of how those two models necessarily interact, but I think the real key is just looking at how the loss function is calculated in many cases. And if that loss function can be differentiated, then you can construct a specific tailored minimization problem to sort of create your adversarial examples off of. In our case, we had the simple CTC loss, which obviously would probably be somewhat easier than a joint model. I could also see maybe a combination of attacking the two individual models. However, I'm a little bit less familiar with how that approach would be executed.
Yeah. Okay. No, that makes sense. Are there other questions or anyone else who wants to ask a question live?
All right. Well, if there's no other questions, we'll definitely answer any questions that you guys have later in the Slack channel. But yeah.
Okay, great. Thank you very much.
All right. Thank you.
So we are now on to our next paper. This paper is minimum norm adversarial examples on k-nearest neighbor and k-nearest neighbor based models by Chawin at Berkeley. Are you able to speak?
Yes, yes.
Very good.
All right.
Do you want to try and present your screen?
Yes, yes. Give me a second.
Sure, yeah.
So this would be. Cool.
I
Can you see the screen now?
slide 2, yes. Yep.
Okay.
Okay, well, very good. Take it away.
Sweet. Thank you so much. All right. So I guess good afternoon, everyone. For at least for those in the Pacific time zone. My name is Shawin Sitavarin. Today it's my pleasure to be presenting our work on minimum norm adversarial examples on k-nearest neighbor and k-nearest neighbor based models. It is 6 a.m. in the morning where I am right now, so please bear with me if I start to make any mistakes. All right, let's get started. So the main goal of our work here is that we try to come up with a tool for evaluating the robustness of k-nearest neighbor on large databases in a scalable way. Oops, I think I missed a slide. Sorry, I think, give me 1 second. Okay. Yes, sorry about that. Yeah, so the problem of evaluating the robustness is essentially we're trying to compute an exact or the minimum norm adversarial examples, or essentially by solving the following optimization problems. We're trying to minimize the L2 norm of the perturbation such that our perturbed sample is misclassified. Unfortunately, solving this problem exactly for k larger than 1 is very difficult. The complexity is exponential in k. And so what we are trying to do here is we're gonna try to approximate it and compute its upper bound, just like how adversarial examples are computed for neural network. First, let's, I think I missed a slide again. Excuse me. Yeah, so first, I'll give really brief introduction to k-nearest neighbor and Voronoi diagram. So k-nearest neighbor, given a query, it's supposed to return k entries or k data points from the database that are closest to q. The distance metric that we use here is Euclidean distance, and we are particularly interested in k-nearest neighbor that we can use as a non-parametric classifier. So basically using the majority vote from the k-nearest neighbors. This classifier essentially also partition the input space into a union of many polytopes, or so-called Voronoi diagrams. The figure below shows the Voronoi diagram for k equal to 1 for several points from two classes, the red and the blue. Now let's talk about other related approach. The first one is solving the QP directly. So this is proposed by Yang et al. And Wang et al. Last year. So let's see that the Voronoi cell of any order k is a polytope. So to find another example is basically we want to find the nearest distance from the query to any of the adversarial cell. So this problem is essentially trying to compute the projection to a polytope described by a set of linear inequalities, ax less than or equal to b, and this is a quadratic program. The objective is a quadratic, and the constraint is linear. It is a really nice, simple formulation, which there are really efficient solutions. Regardless, there are still some issue. So issue with this approach is that we have to solve a lot of QPs. We have to solve as many QPs as the number of adversarial cells. This can be really bad. Suppose your data set has 1 million data points. So n is about 1 million. For k equal to 1, the total number of cells is n. So this is not too bad, but for n larger than 1, the number of cells is at most n choose k, or n to the power of k. And also, this actually can be a little bit worse because solving each QP you have to solve a lot of QPs, and each QP has k times n minus k constraints. So this also increases with k, and complexity of solving a general QP is polynomial in their number of constraints. So Wang et al. Introduced some really cool tricks that speed up the optimization significantly. So they managed to run this exact attack on a full-size MNIST dataset, which is about 60,000 points for k equal to 1. For k larger than 1, though, this is still really difficult. So both of the works have to introduce some heuristics, which can only compute some loose upper bounds. There's no exact method there. A second line of related works is proposed by Li et al. To use transfer attack. So what they do is they train a neural network to imitate the behavior or the class probability of the k nearest neighbor, and then they apply well-known like PGD attacks on the neural network, and then try to transfer the adversarial examples to k nearest neighbor or k nearest neighbor based model. Of course, this would require sampling from the target network and requires training a whole neural network. So it's going to take time to set up, but to compute the attack, it's pretty fast, and unfortunately, still the bound could be pretty loose. All right, now on to our attack. So really a brief introduction here is that for this talk, we are only going to consider the binary keys or binary labels. So -1, 1, and we define dk of q as distance from q to its kth neighbors. So prediction of this queries can be written as like a sign of sum of labels times some indicator functions. And this indicator function is really simple. It's basically just say, okay, if my entries or x, which is the data points, is one of the k nearest neighbors of q, then it returns 1. Otherwise, just returns 0. And then you can sum this up for your entire database. So now we set up our attack as an optimization problems. So our variable here is the perturbations, and or delta in this case. So we try to minimize the L2 norm of our perturbation such that the perturb sample is misclassified. We don't want to deal with the constraint, so we use penalty method to deal with it. But still, this problem is still really difficult to solve because indicator function is non-differentiable, and so we have to try to approximate it somehow. So last year we tried to approximate this indicator function with the sigmoid, and so we arrived with this formulation. We write eta as instead of dk of q plus delta here to shorten the notations. But there are some issues with this because as we all know, sigmoid has some underflow and overflow problems. So in this work, we basically replace the sigmoid with a hinge loss. So now it's piecewise linear, and it no longer has this underflow or overflow problems. We have to do some rearrange, and at the end we arrive at the formulation below. And now on to the second issue. So there's still some issue with our formulation, which is right now in the objective function, we are computing this loss on the entire database. Notice that we have to sum this for all xi for all data points in the database. So this is still really expensive to compute. And essentially, we actually don't really care about data points that are far away from Q, right? Because we only consider we want its K nearest neighbor. And so solution to this second issue is we can introduce some heuristic to only pick a subset of M nearby data points, and we call these guide samples. And we want the size M to be a lot less than N. And essentially, we pick half of them from class -1 and the other class from class 1, and all these are like quote unquote really close to Q. So now we sort of deal with our second issue. Another issue here is that, so the third issue is so far we have only been treating eta or distance from our perturbed sample to its kth neighbor and the guide sample that we just introduced on the last slide as some fixed quantity. But actually, in fact, they are a function, a non-smooth function of delta, and they are quite expensive to compute. And so their gradient is going to be expensive to compute as well. So we want to make it faster. We kind of noticed that we only update this delta in a really small step. Essentially, so these two quantities don't change very much during the optimization, or don't change very fast. So our solution to this third issue is that, okay, let's say we can only recompute this eta and the guide samples at every some certain step of the optimizations. And so we deal with all three issues that we have right now. They're quite simple. They're not really hard to solve. It's only take about one slide each to solve. And so we want to give a really rough complexity analysis, I guess, for our algorithm. So it seems like our algorithm doesn't depends on K and N from the formulation, but its dependence is kind of hidden. So K, the dependence on K is hidden in M because we have to choose M to be larger or equal to K, or roughly in linear of K. And dependence on N is hidden in the computation of eta and the guide samples. So naively, we can use a linear scan to compute these two quantities, and it's going to be a linear in N. So really roughly, our complexity is about O of N times K is linear in both of them, instead of O of N to the power of K for the solving exact QPs. I say that this is really a rough approximation because we have ignore like a lot of factors. We have ignore the number of dimensions, ignore what optimization algorithm we use, and the convergence of this algorithm, like how many number of iterations we have to take. It is also worth noting that the objective is decomposable, so it's a sum of many terms, but they can be computed in parallel. So when we implement this on GPUs, we don't see the factor, the increase in runtime with K, because it can be parallelized for multiple M's. Also, it can be parallelized for multiple queries. So it's really efficient in that sense. Okay. Now on to the result on K nearest neighbors. So we use our method along with the Yang et al. Implementation to evaluate robustness on K nearest neighbors for multiple Ks, for K equal to 1, 2, 3, and 5. This is on only 2 class MNIST, so I believe it's class 3 and 7, or 3 and 5, I think. But okay, for K equal to 1, Yang et al. Performs really well. It finds the exact minimum norm perturbations. but it can take really long time. So 30 hours, up to 30 hours for the exact method, and only 2 hours for the approximate one, which turns out to find the exact perturbations. For ours, it doesn't find as small of a perturbations, but it's only take 5 minutes. For k larger than 1 though, for in this case k equal to 3 and 5, now our method outperform approximate method in Yang et al. So we managed to find smaller L2 norm of the perturbations with only still about 5 minutes, for the reason that I mentioned earlier, that it doesn't really scale with k. And now Yang et al. Has to use much more computation time. Essentially, the approximation will exponentially, they'll miss exponentially more adversarial world noise cells as k increases, in order to keep the runtime only like polynomial in k. So benefit of algorithm is going to be certainly more significant as k increases in terms of both time and the tightness of the bound. Now let's move on to the second part of our attack. Which is the attack on the k nearest neighbor based neural network. So in the past couple of years, people tried to combine k nearest neighbors and neural network to come up with some sort of a defense or interpretability technique. So we are so interested in that line of work, so we're trying to come up with the defense as well. And so we create this attack to evaluate a defense, and indeed we kind of break it. And so here we're gonna evaluate 3 defenses on MNIST, and note that the QP methods actually no longer work for this neural network based, for k-nearest neighbor based neural network, because while they use k-nearest neighbor on the representation space, but then in the input space, the constraint is no longer linear, or it's no longer the convex polytope. So it cannot be solved with QP anymore. All right, and let's see the first model here. So the first combined model here is we use k nearest neighbor on 1 layer of the neural network's activations. And so we have a pre-trained network, and then we take 1 layer and do k nearest neighbor search on it. So this actually requires really minimal change to our formulations. We only have to introduce this neural network function, which is written here in red as f. So f is, you can think of it as some transformation that is differentiable. So we're trying to solve this optimization with first order method, or just computing gradient anyway. So when it's differentiable or subdifferentiable, this poses no problem at all. So it's really highly compatible. For another defenses that we evaluate here is the deep k nearest neighbor, which is generalization of the previous one. So instead of taking only 1 layer, you can imagine we can take multiple layers or all of them, and thus this k nearest neighbor search for all of them separately. And to make our objective compatible, we just have to sum our loss across all the layers. The third defense that we evaluate here is basically just apply PCA to reduce the number of dimensions on the network representation. And PCA can be, seen as a linear transformation. So it's just a linear transformation on top of some differentiable function, right? So everything is still differentiable. So we just have to introduce this transformation matrix, and everything is everything still works with our method, basically. So let's see the results. So we evaluate all these three defenses on a full MNIST data set. And so we have a pre-trained network, just trained it normally. And we also evaluated with Cardini-Wagner attack. And you can see that most of the defenses actually improve the robustness. I mean, according to our attack anyways. So the L2 norm perturbations, as you can see here, L2 norm perturbation here is larger than the network without the k-nearest neighbor. And also, so I mean, these schemes to help. This scheme seems like they help improve the robustness of the undefended model, and also k-nearest neighbor. So we also compare it to k-nearest neighbor for k equal to 5 without any network, and that actually also seems quite robust. And one thing to notice is that we compare our new and old scheme. So our new scheme outperform our old ones in every setting, basically. And so we thought to ourselves, okay, perhaps if our base network that we're going to use with the k-nearest neighbor is more robust, then maybe we can improve their robustness when we use it with k-nearest neighbor as well. So what we try next is we adversary train the models, and then we use it with these defenses. Basically, just apply some k-nearest neighbor scheme on top of them. So we initially thought that doing this can be a really promising defense, because according to our old attacks, they seem to be more robust than our baseline here, which is the adversarial training by Madhu et al. So you can see here that seems more robust. It has higher L2 norm with also higher clean accuracy, right? So it's better in both sense than just normal adversarial training. But we thought to ourselves that this is too good to be true. So that's why we come up with this new attack. And it turns out that when we use this new attack, it's no longer, these defenses are no longer more robust. So that's kind of highlights how important having good evaluation is for this field of research. And I think that's most of it. To summarize, we develop a gradients-based attack that is compatible to both k-nearest neighbor and k-nearest neighbor-based neural network. It provides a scalable way to evaluate these models on a large database with k larger than 1. And in this case, it's much more efficient than the QP-based methods for k-nearest neighbor, especially for k larger than 1. We also use it to evaluate previously proposed defenses on neural network that uses k-nearest neighbor as components, and it turns out that none of them are more robust than adversarial training. For future works, we still see k-nearest neighbor as perhaps a naturally robust classifier. So maybe there is some better way to combine it with neural networks. And I think that's it. Thank you. I'll be happy to take any questions.
Thanks. So it looks like there are 2 questions for now in the chat. Are you able to see that?
Let's see.
Actually, let me see if I can get Jonathan. Jonathan, I'm going to make it so that you can speak.
Okay.
If you want to ask your question live, you can go.
All right. Hello. Thank you. Thank you. So, yeah, my question, the first one was about the hinge loss instead of the sigmoid. So it was like, can you explain again what was the benefit of using the hinge loss instead of the sigmoid?
Right. Yes. Yes. Yeah. Let me try to find a slide. It might be easier to see. Yes. So sigmoid function has, it has exponential term in it. So it has known issue of like numerical unstable when the input is really large or really small, like, so it could go to 0 or go to infinity, and that could be the case here because this term, this L2 norm could so we basically just compute different an L2 norm here, right? So it's not bounded in any way, and so this term can blow up. So it can be like, let's say like 10, 20 is fine, but if it's like close to more than 50 or 100, so then you take exponential of negative 100 or 100. So it basically gets to 0 infinity, and it doesn't have gradient anymore. Does that answer your question?
Yeah, so why the hinge loss was
right.
for you
Yes.
the answer?
So hinge loss also sort of approximate our indicator function, and it does not have this overflow or underflow problems as in sigmoid. And so we don't like directly apply hinge laws to like replace hinge law with sigmoid, because there's some region with 0 gradient, so we have to rearrange it a little bit. And yeah, but you can see more detail from the paper. But essentially now we no longer have the gradient problems. Yeah.
Got it. And so the second question I had in the Q&A was, maybe I missed it a little bit in your talk, but did you show the gradient-based attack like effectiveness on the KNN? Just on, so I have a KNN, now you're doing your attack, because it seems like in your presentation you said we came up with the attack, and then you talked about the defense, and then now you're looking at all the defense. Maybe I missed that, so I apologize if I did. So I'm kind of asking you again, what was the effect on known of your attacks? And I can see actually slide 16.
Yeah, so sorry. Yeah, I just pulled up. Yes, so this is evaluated on so this evaluate, like, it compares different attacks on normal k-nearest neighbor on MNIST. So we have to pick only 2 class MNIST because Yang et al. Method will take much longer. We just we more recently found out another implementation from Wang et al. And for that, it actually runs much faster than this. But the problem for this method is that they don't. It's very difficult to scale for k larger than 1, and in practice, we usually use pretty like sizable k, maybe 10 or even to 100. So our method is very nice in that sense that it scales really well with k. So it's with larger k, our method also runs slower, but it scales in a much nicer way, and we usually get a much better. We usually find a much smaller perturbation.
Okay. Thank you.
Thank you.
Okay, well, thank you again, and especially I'll echo Matthew from the chat, and thank you for waking up so early to give this presentation live. So let's move on to the next talk, which, as it turns out, is another talk from Berkeley. This one is Clipped BagNet, defending against sticker attacks with clipped bag of features. And for those of you who were here this morning during Wayland's keynote, this is a nice application of one of the methods that Wayland developed.
All right. I'm going to share my screen.
Very good. Yep, I can see.
Cool. open up. Cool. So can anyone see the presentation mode of the?
Yes, we can hear you too.
Sounds good.
Okay, go ahead.
All right, let's get started. So hi everyone. My name is Zhan Yuan. I go by Sean. I'm today to present the Clipped Backnet, which is a defense we propose to defense against adversarial stickers attack. And first of all, let me just briefly show you what adversarial stickers are. So adversarial stickers are usually unnoticed to us, and they do not change human classification of an image. But these small areas do change the classification of models, especially neural network models. And if you look at the leftmost image, we think that this is a water hose, but the model thinks that it is a ptarmigan. And in the second left image, we human thinks that it is just a dog, but the model thinks it is a dog wearing a muzzle. And in the right image, some other researchers show that the adversarial stickers can make a person invisible in front of a AI camera. Yeah, so as you can see, adversarial stickers can exist in both the digital and physical worlds. Compare with a canonical adversarial sticker, adversarial examples, it's pretty clear that adversarial stickers can easily be printed out and then deployed in the physical world. So it's more practical. And in fact, many other AI systems, such as face recognitions and autonomous vehicles, are threatened by these adversarial stickers attacks. So our goal is to improve the robustness of a classifier under such sticker attacks. So our method is based on the vanilla backnet, which was explained by one of the original authors, Dr. Brando, in his keynote presentation. Appreciate that. I'm gonna briefly explain it here again. So backnet is a brilliant idea that breaks an image into several patches and forces the neural network to only process the local features within these patches by limiting the size of the receptive field of each convolutional neuron. So at the top of the backnet, each patch gonna generate logic for each class. And by aggregating the output of all the patches, in this case through averaging, we get the final score of each class. Then we make decisions based on these scores. So I now want to walk you through several examples to demonstrate the difference of the vanilla backnet and our Clipped backnet. Let's start from a benign case. So no adversarial stickers in the image. And we're gonna focus on 3 classes, C1, C2, and C3. And record that each of them has a logic matrix, which is also called the heat map in the original backnet paper. And then among those logic matrix, the entry at the same position are given by the same patch. So, so for example, 20, 19, and 25 here are given by the same patch. And for vanilla backnet, we simply average the number in matrix to get the final score of each class. In this case, vanilla backnet gave the correct prediction. And for our Clipped backnet, we first applied a monotonic increasing clipping function to clip the values in the matrix from -1 to 1. And then we apply averaging. And so since the clipping is monotonic increasing, our Clipped backnet won't affect the clean accuracy too much. And we also apply some scaling and shifting before the clipping for adjustment. Now let's consider an adversarial case. So there's adversarial stickers which increase the class C2, one of the patch, like from 18 to 34. And the vanilla backnet is gonna just average the logic and then misclassify the output, get the wrong prediction. However, if we clip the values first, then the effect of the sticker is limited. And in this case, our clipped backnet still classified the image correctly. And so the effect of clipping is twofold. Not only does it limit the effect of an adversarial stickers by bounding the logics, but it allows us to provide certified security. Now, this is important because no matter how good we are at attacking our own system, someone else may be better. So we instead need to evaluate against a theoretical adversary and provide a certified security. And specifically, if we know the position of the sticker, then we can calculate those patches affected by this sticker. And by letting the logics of all the classes and setting them to 1 and -1 within these affected patches, we get the upper bound and the lower bound of the logics of all the classes. Then we say at this particular sticker position, the image is certified secure only if all the classes, only if the lower bound of the true class is strictly larger than the upper bound of other classes. And remember, that's only for one sticker position. So an image is said to be certified secure only if it is certified secure for all sticker positions. Yep. And now I'm presenting the experiment results of our method. We sample 500 ImageNet image and crab sticker of size 20 by 20. And we evaluate against both targeted and untargeted attack. So in targeted attack, the adversary goal is to push the targeted class to the top, while in the untargeted attack, the adversary's goal is to push the true class out of the top 5 prediction. And I present the data here because it has the best top 1 and top 5 clean accuracy among the undefended models. And as you can see, the vanilla backnet is slightly better against sticker attacks, but the robustness is significantly improved after we apply clipping. And finally, we also conduct a black box attacks to make sure there's no gradient masking issue. Here is the scatter plot of, so the x-axis is the PGD loss value, which is, PGD is a white box attack. And the x-axis is the loss value at the 500 iteration. And the y-axis is SPSA's loss value at 500 iterations. And SPSA is a black box optimization algorithm. And as you can see, most of the points align on the line of y equals x, which means these two algorithms, both black box and white box, they converge to nearly identical values. So back in the time while I was working on this paper, there were many other papers on defending against sticker attacks. But now I'm happy to see that more related papers are showing up. I mentioned some of them in the paper, but here are the 2 most recent ones. And I'm willing to talk about this in the Q&A sessions, but just briefly mention that. So for example, for the for the first one, the adversarial training against location optimized adversarial patches. One of the advantage in this work over us is that they propose a pretty good heuristic to find the optimum, quote unquote, optimum location for the sticker to apply. Instead, in our work, we just brute forcefully iterate through all the possible position with certain stripe. And another work by Michael et al. On the minority reports defense, they also provide a pretty good, interesting way to defend against adversarial seekers. And if I remember correctly, one of the differences is that, they also provide certified security, but they kind of slower in terms of computing the results, because their methods kind of involve iterate all the possible position during the inference time, and versus our methods is just the normal evaluation, but with the clipping. Yeah, I also noticed that our method does not involve any kind of extra training or fine-tuning on the model. The only requirement is that the model should rely on local features or backup features. Yeah, so here's a summary. We try to solve the problems of adversarial stickers, and our approach relies on clipping backup features. And we improve the robustness against state-of-the-art attack, aka PGD, projected gradient descent. We provide certified security on ImageNet with 20 by 20 stickers, especially for the targeted attack. We have 95% robust accuracy and 25% of unrobust accuracy. And we also do black box attack to show that there's no gradient masking. Yeah, I can accept any question now. Q&A session.
Great. Thank you very much.
Thank you.
So it looks like we have one question from the Q&A from an anonymous attendee. And it asks, in the evaluation, did you digitally attach adversarial patches to the images, or did you print out patches and take the photos of the objects with the patches in the physical world?
Oh, so all our experiments are done on digital world, and we craft the stickers just with the adversarial algorithm on this position.
Okay. While we see if we get any other questions, I actually had a question. So your results for top one, your robust accuracy was 99.8, I think. And for top five, it was like 60 or 70%.
That's right.
I would have expected that it would be like 5 times harder or something to go to top 5. And the accuracy would be like, I don't know, 99 instead of 99.8. Why does it go down to 65? This seems more than I would have expected.
Oh, so notice that this is for the untargeted attack.
Ah, I missed that.
Yep.
Okay.
So for the ImageNet, because it's kind of such a big data set, it's kind of noisy, people usually use top 5 prediction as the...
Yeah, okay. That makes a lot of sense. Okay, thank you very much. So there's another question from the chat. Let me see if I can unmute. So Tong, I've allowed it so that you can speak if you would like to ask your question.
Yeah, my question is simply, would the method could generate to like 2 or more patches attack, like instead of just 1 patch?
I believe so. So even though we did not investigate on that, and I don't know if that would work. So if you notice that even though we only have one sticker here, and because
Yep.
our classifier only depends on the backup feature, you can imagine that you could have multiple sticker. And I assume that the area of these multiple stickers should sum up with the same size as the same one. If you try to like come up with a comparable result. Does that make sense?
Okay. Yeah, thanks.
So, and also the shape of the sticker is also can be very flexible. We only use square here, but you can use anything else. As long as you can calculate like what are the affected patches.
So it looks like there's another question from an anonymous attendee in the chat. Have you ever tried patches with different size? It seems like small patches are harder to be detected.
Oh yeah, so in the paper, we also evaluate against some other size of the patches, especially for our certified security. You can find more details in that. And yes, with the smaller sticker size, the accuracy, the robust accuracy is higher as we expected.
Sorry, to clarify, with a smaller sticker size, your defense works better. Is that correct?
Mm-hmm.
Okay. I guess the question was saying it seems like smaller patches are harder to be detected. So I guess
Yes.
maybe the person who asked this question thought the reverse, but.
Yep, we are not going to detect the sticker. And we believe that detection should be another line of work, which I'm also interested in. And
Okay.
I remember one of the related work by McCoy, the Minority Reports, they propose a way to detect the adversarial stickers. You can look into that.
Great. Any other questions on the chat? Okay, well, thank you for coming to give this talk.
My honor. And I'll also wait in the Slack channel for questions.
If there are any other questions, feel free to message the speaker in the Slack channel.
Mm-hmm. All right.
Okay. So with that, we are now up on the last paper in the last session of the workshop. So this is a paper called Sentinet, Detecting Localized Universal Attacks Against Deep Learning Systems. And it tries to do a similar kind of detection strategy as the previous paper. And so it will be interesting to hear the two right after the other. Edward, are you able to speak?
I'm here. My internet's
Great.
a little choppy, so hopefully everything.
We will bear with you. I have had several problems throughout the day as well. So
yeah. Okay. Thanks. Let me try to get everything. Okay. Is that working?
yep, I see your screen.
Okay, cool. So hi everyone, my name is Edward, and I am presenting our work Sentinet, Detecting Localized Universal Attacks Against Deep Learning Systems for DLS 2020. This was a work completed with a lot of help and guidance from my co-authors, Florian Trommer, who's on the call, and Giancarlo Pellegrino. So in this talk, I'm going to go over the background and motivation of localized universal attacks and how our architecture detects and classifies these attacks in a novel attack agnostic fashion. In our experiments, I want to show how our attacks work on techniques with very different mechanisms and how it is also resistant to adaptive adversaries. Then I'm going to close with some concluding remarks. Adversarial attacks are pretty well known in the deep learning and security community, but I'll cover the basics. Neural networks are vulnerable to adversarial noise, where techniques such as FGS can create perturbations from gradient-based optimizations to full neural network classifications. So usually these noise are L2 normed, so it is undetectable to the human eye. And we can see examples like here, where an image is classified as an airliner, even though it is very clearly a pig to a human viewer. Over the years, researchers have developed a wide variety of other techniques for adversarial noise, including white box and black box attacks, and using different approaches such as evolutionary algorithms, data poisoning, and etc. So localized universal attacks are a specific subset of deep learning attacks that does not attempt to make the added noise invisible to the human eye. Instead, these constrain the pattern to a small region of the image. The universal tag of this approach covers the class of attacks that always directed the network towards a particular classification label, regardless of the targeted image. These types of attacks are much more suited for real-world deployment, where it is difficult to apply invisible noise over an entire image. For example, if you wanted to fool a self-driving system, you could print out an attack on a sticker and apply it over a stop sign. Or if you wanted to fool a building's facial recognition security system, you could wear glasses with an attack overlaid on the frames of the glasses. And as with regular adversarial samples, there are many different mechanisms for deploying localized universal attacks. We'll cover three distinct approaches that we demonstrate on our work, Sentinet. The first is Trojan attacks from Trojan attacks on neural networks by Liu, which combines adversarial noise with fine-tuning specific neurons in the network to activate in the presence of that noise. The second is backdoor attacks from BadNets by Gu, which poisons a network towards a specific classification when a specific pattern is seen. And the last is adversarial patches by Brown, where adversarial noise is generated without the L2 bound constraint. And one particularly notable aspect of this attack is that it is a black box attack against all ImageNet trained models. Here's a visualization of the three attacks. As you can see, the localized noise varies widely between the three, from colorful patterns to actual flower-like patterns. One thing to note is that these attacks usually attempt to be innocuous to the average person because these small patches are added to the corner or edge of the image and won't detect the decision-making of a human. These distinct mechanisms poses a huge problem in our threat model. Both poison networks and Trojan networks have patterns that affect only that particular network. So tracing a universal adversarial detector is pretty much out of the question. Also, the Trojan network shows that it is possible to introduce these vulnerabilities very late into the model deployment chain, even when the attacker does not have access to the training process at all. And some localized universal attacks could be black box, meaning that our model is still vulnerable even under the most secure training and deployment procedures. We're operating under an assumption that the user has no idea where the model is from and what vulnerabilities could have been secretly added, or even what the attack will look like or what mechanism it will use. So this will affect downloaded pre-trained models from the internet or models exposed on camera hardware. There are many works that have attempted to defend against adversarial attacks, both for localized and non-localized attacks. A common approach is adversarial training, where a network is trained adversarial samples to increase the robustness of the network. Another set of approaches involves training machine learning detectors, such as object detectors and SVM classifiers, nice adversarial samples. There are several problems with these approaches. A main one is that the defender will often need to have existing samples of the attack beforehand, either to train the network or to train a classifier. Alternatively, the user will at least have to know the mechanisms of the attack in order to generate plausible samples to train on. In addition, these techniques are often vulnerable to adaptive adversaries. An adaptive adversary can optimize on an adversarially trained network to generate further adversarial samples, or generate adversarial noise to fool an object detector or classifier. This is a huge problem in the machine learning and security field in general, where adversarial attacks and defenses are often pitted against each other in an arms race. With this threat model and the limitations of existing defenses in mind, we want to address two main points that we want our system to achieve. We want to develop a defense that will work without any known samples or knowledge of the mechanism of the attack. And we want the system to be resilient to adaptive adversaries with continued and full model. The intuition of our methodology would be to understand the underlying mechanisms of how the adversarial samples are affecting the system. There's a chance that neural network visualization techniques such as GradCam could also determine which regions of the image are most influential towards the model's prediction, and that this information could be used to determine whether the image is adversarial. This is the fundamental approach and motivation of Sentinel. I'll begin to cover the methodology of our system. At a high level, we use GradCams to localize the region of the image most responsible for an image's prediction, segment that region, and overlay that region to other images before feeding these overlaid samples back into our model to collect statistics that will help us determine whether that image exhibits adversarial behavior. We can split this method into 4 basic steps: class proposal, where we evaluate what are the top ranked classifications of our original image; mask generation, where GradCam is used to segment the region; test generation, where we overlay the region onto other images; and then boundary analysis, where we curve fit to determine whether the image is adversarial or not. We want to collect 2 values from our model to perform our curve fitting. The first is the percentage of images fooled when we apply the GradCam region and feed the images through our model. The second is the confidence of the prediction when we apply the error to images, but replace the context of the region with random noise or pattern. With these 2 data points, we believe it is possible to distinguish adversarial and non-adversarial regions based on the network behavior alone. Non-adversarial regions that take up a huge portion of the image could cause misclassifications on a lot of images by virtue of replacing the majority of the target image. But when that region is replaced with noise, the confidence of the model should also drop significantly. Meanwhile, non-adversarial regions that take up a small and unimportant part of the image will not cause many misclassifications, but will also not impact the confidence much when replaced with random noise or patterns. Only adversarial regions will be able to both fool a lot of images when overlaid on the test set and not affect the confidence of the model when replaced with noise. As you can see, this allows us to draw a decision boundary when we map the confidence on the x-axis and the fool rate on the y-axis. The red dots in our image are adversarial regions that have both high fool rate and high confidence with random patterns. And the regular images all fall somewhere between that extreme, with more trade-off between fool rate and noise confidence. A nice property of our approach is that no training is required and no previous examples need to be seen, and also that the mechanism doesn't need to be understood. We can simply collect data points on benign samples and use nonlinear least squares to approximate the decision boundary of the benign samples and classify points outside that bound as adversarial once we establish a good baseline for how regular images should behave with our model. One additional step of our methodology is to reduce the size of our mask to refine the GradCam region proposal. We can use a modified faster RCNN classification trunk along with a selective search algorithm to feed multiple region proposals through our network to generate top X class proposals. We can then subtract the top X masks from our primary classification mask and take the maximum of the fool rate and confidence rate sum of these mask proposals to use in our decision boundary. This is really helpful when GradCam is highlighting portions of the image beyond the adversarial region. In this case, the Trojan pattern causes the model to classify the image as a certain identity, and the original face plays a role in that misclassification. However, the selective search and classification trunk discovers the class of the original face and gets the mask for that class and subtracts the region from our original mask, which helps us refine our mask to only containing the adversarial region. These plots show how our technique is agnostic to a lot of different mechanisms. We covered before how Trojan poisoning and adversarial patch attacks are all based on different mechanisms and also vary by appearance. However, we can see from these plots that the adversarial and non-adversarial points follow the same trend, where only the adversarial regions have a high fool rate and confidence with noise, and that it is possible to establish a decision curve just by sampling enough benign points. We can see this holds true even when the number of adversarial patterns deployed is arbitrary, which in our threat model the attacker is allowed to do. In this case, our technique successfully captures when two adversarial patches are placed on the image without any modification needed in our technique. Here are the full experimental results of Sentinel's detection effectiveness for a variety of tasks. We'll highlight some of the important results of our model. For Trojan attacks, we get over 99% true positive and true negative rate for adversarial detection, regardless of the noise added. So either checkerboard or random noise. For adversarial patches, we get over 95% true positive and true negative rate. And for backdoor attacks, we get over 85% true positive and true negative rate. These are relatively good results in comparison to other works detecting images with adversarial content, where true positive and negative rates are listed starting from the 70% range upwards, as seen in the work Evaluation and Design of Robust Neural Network Defenses. So now we know our technique is effective at detecting adversarial samples. The next question we want to ask is whether any components of our architecture are vulnerable to adaptive adversaries that have full awareness and access to our system. Looking at our system, there are many parts and components that an adversary can target, and we need to show that all of them are resistant to adaptive attacks. A huge component of our system is GradCam, and we need to make sure an adversary can't just introduce noise to break the region proposal. One straightforward way to break GradCam would be to point the highlighted region to another part of the image. We start by performing a set of experiments to optimize on GradCam outputs with a specialized loss function. In the leftmost image, we see the heat map of the adversarial patch shows up on the bottom right portion of the image, and we want to see if we can recreate that heat map with adversarial noise. You can see that perturbing on all the pixels in the image will allow us to create a heat map identical to the target output. And if we are allowed to perturb on the bottom left portion of the image, bottom right portion of the image, we can still produce the desired heat map output because it's in the same local region. However, if we're not allowed to perturb on the region of the image we would like to influence, we cannot reproduce the heat map. On the rightmost example, we're only allowed to place noise on the top left portion of the image, and the heat map is completely wrong. This shows that affecting a localized GradCam output requires modifying the pixels in that region directly, since GradCam preserves spatial mapping from the pixels to the heat map. Next, we can attempt to create a patch that doesn't show up on GradCam but still fools the network. We show that we can optimize for a loss function that creates a patch with minimal effect on the GradCam heat map. So that's the image of the green patch to on the third image from the left. However, when we try to jointly optimize for both GradCam minimization and full rate, we find that these two objectives are in direct opposition with one another. Here, we try scaled weighting for hiding the patch and fooling the network. The left green patch is fully optimized towards GradCam minimization, and the right patch is fully optimized for fooling the model. We can see from our curves that the ability for the patch to successfully hide and fool the model are inversely related to one another. And near the center of the weighting ratio, the probability of the patches to perform both objectives is minuscule and cannot be deployed as a reliable attack because it has a high chance of both being detected by GradCam and failing to fool the model. Next, let's think about whether adaptive adversaries can affect the class proposal step of our. We used the original network to perform class proposal. So we have a nice property where the adversary won't have the opportunity to fool a separate class proposal network without also fooling the target model. In addition, selective search is not a gradient-based technique, which means there is no loss function to optimize on, resulting in the algorithm being difficult to attack. Finally, our technique considers both reduced and non-reduced masks and collects data points for both. So attacking the class proposal stage of our defense won't allow the adversary to bypass the defense altogether. And we consider whether the adaptive adversary can affect the decision boundary step of our approach. We operate under the assumption that our defense will be able to choose and keep the benign set, and that the random noise and patterns are kept secret. So the defender will be unable to exploit these components of the system. Therefore, the curve we generate from the benign samples cannot be manipulated by the adversary. And because our curve is generated without known adversarial samples, we have the attacker doesn't have a traditional SVM or gradient-based classifier to exploit. Now we go over one adaptive adversary attack that can be deployed. With an attack on a huge region of a network, it is possible to achieve high folding rate and low confidence, which will bypass our defense. However, this brings up a question of what constitutes adversarial attack. This is a question that the authors of the adversarial patch paper grappled with as well. Essentially, we could achieve the same effect of an attack by placing a large image of the target class, and in this instance of toaster, over the target image. In essence, our system doesn't defend attacks that overlap a huge portion of the target class, but we can see through other works on localized universal attacks that the real threats occur when the adversarial region is both innocuous, yet has a profound effect on the network, rather than an image that works by obfuscating a large portion of the original image. So we can see that there are many strengths of our approach. We are able to turn a weakness into a strength by utilizing the fact that our model is fooled directly into our adversarial detection decision and our boundary curve. In addition, we utilize model understanding techniques within our system, explores at a more fundamental level what causes a model to make a decision and get fooled by an adversarial attack. And both of these aspects are what directly leads to both the attack mechanism agnosticism and robustness to adaptive adversaries. However, our approach does have some weaknesses. We only cover universal attacks in our work, and we will need another method to quantify when a model is fooled, when the model classification is different is non-targeted. Also, there is some latency introduced with our approach from 0.04 seconds with a normal forward pass, which could be batched, to 2.5 seconds of sentiment processing time, which is not completely optimal for real-time deployment. Future to explore could be to utilize better network understanding techniques, such as GradCam++, and see how much sentiment benefits from more recent network visualization techniques. We're also considering handling non-universal attacks by quantizing the fall rate through the neural outputs of our model. So that's related to some of the works previously presented today. And finally, we would like to explore reducing the computational cost of sentiment. And some obvious candidates to optimize includes the selective search portion of our algorithm, which is a relatively expensive operation. And that concludes my talk. Thank you for listening, and we look forward to any questions you might have about our work. Thanks.
Thank you very much. So it looks like there's one question on the chat, and feel free to ask others as we go through this one. So the question says, some ML literature shows model understanding tools like GradCam and its family are not reliable. I'm curious, in your case, do you always find that GradCam is able to detect the desired region?
In our case, it is reliable for our purposes because the adversarial regions tend to have to override a lot of the other portions of the images to cause that classification label. And so that region tends to be completely responsible for the outclass, the prediction, and GradCam picks up on that really well in our experience.
Do you think that it would be possible to design a single patch that would simultaneously fool GradCam and also the classifier?
So a lot of our experiments were trying to show that it wouldn't be. Like, especially the experiment where we tried to jointly optimize for hiding from GradCam and redirecting from GradCam, redirecting the output. There might be, yeah, I think there's definitely, it's an open question whether it's possible.
Yeah.
But yeah.
Okay, maybe let me ask one more then. So the same question as was for the last talk. What would happen if you had two patches?
So for two patches, it depends a lot on the GradCam behavior. So if there's two patches that target the same class and GradCam successfully picks up on both of them, then our attack should work properly. But there's a lot of different configurations that the attacker could implement. And for example, like placing patches for different classes or using patches that are interrelated within one another. And then I think a lot of it will depend on how fine-grained the GradCam heat map is, which is why exploring further directions like GradCam++ or better visualization techniques would be a great direction to explore.
Yeah, that makes sense. Any other questions?
I'm wondering, what if you, like, have you tested on different sizes of the patches?
Yeah, for our experiments, I didn't cover this, sorry, but we tried to randomize the size of the patches within our experiments. So it works really well up to the point where the GradCam resolution, which tries to divide the image into a 7x7 grid. Once it falls below that region, then there's some risk that like our GradCam selects too large of a portion of the image, segments it out.
Thank you.
Maybe final question though. At the very end, you put a note that it was maybe 4 seconds for inference. Is like, where does this inference time come from? Is it spent in GradCam or is it spent in something your defense does?
So GradCam and inference, there's some time spent there. Those two cannot be optimized by GPU, but one big portion is selective search, which is a more deterministic, like, based algorithm, and that was used in the initial like RCNN detection works before faster RCNN were introduced. So a lot of time is spent on the selective search portion, actually.
I see.
Yep.
Okay. Well, it looks like there are no more questions then. So thank you for presenting. And this concludes the final talk of the final session. So thank you all for sticking with us. Nick, if you want to.
Yes, thank you very much for participating. That was the third DLS. I just remember right now that Nicola was the very first speaker of the first DLS 3 years ago. It's really interesting. We had a record attendance. I think at some point we reached 130, 140 people. Thank you for some of you for staying late. And we hope to see you next year. If anyone wants to take over or participate in the organization, we'll please reach out. Yeah, we'd also like to thank our sponsor Avast for sponsoring the event for a third consecutive year, and Gabriela for doing all the hard work behind the scenes to help us with organization in these challenging times. Stay safe and secure. Thank you. Have a good weekend.
Thank you, everyone. With luck, we'll do this again and we'll be able to meet in person.
Yes, next time.